So why on earth would anyone study history and philosophy of science? What's the point? I'm going to tell you the story of the 17-year-old Jakob. Oh, not this one. This one. 17-year-old Jakob. When I was 17, I was a bright kid, and I knew my science. I thought I knew my science. And somebody asked me, Jakob, what do you know about the history of science? Okay, you know your physics, chemistry, and so on and so forth. But what do you know about the history of science? What I would tell back then is pretty much along the lines what every high school kid, probably every talented high school kid, would say in response. This is basically what you find in popular science literature, or you find in science textbooks, or even in professional science accounts. This is what I call popular science mythology. And this is the story of the 17-year-old Jakob, which I think many of you would share. Slightly after the Big Bang, there were these weird guys called ancient Greeks. And these ancient Greeks, they were very, very bright guys because they tried to understand the universe, how the world works, what things are made of, and so on and so forth. But the trouble was they got all of it wrong. For instance, I knew back then, Plato would say that every object is made of tiny, tiny triangles. Aristotle believed that the earth was in the center of the universe. And this guy here, Hippocrates, would teach that human body is made of 4 bodily fluids, whatever those fluids are. And finally, that guy over there, Democritus, he actually believed that education is basically for the unfortunate. It's just one step from saying ignorance is bliss. So basically, this guy's got everything wrong. So it's not really surprising that back then there was no science whatsoever. What was there in abundance? Tons of religion. And the funny thing was that you could actually choose your religion. You could decide to pray to Greek gods or to your Egyptian gods. Or if you were so inclined, you could even choose to pray to the gods of the 7. Old gods, new gods. And you could even choose to pray to the Lord of Light, for the night is dark and full of terrors. But the thing is, this whole fun ended when Christians came along. They provided a religion that was supposed to be good for everyone, you know, one size fits them all. And the whole fun ended. They would teach, you know what they would teach. The God made everything, the universe, the mankind, all living things. And for a very long time, there was no science, just religion, until some heroes of science appeared. And among those heroes was this guy, Galileo Galilei. He was the first brave enough to say everything he thought about the dogmatism and ignorance of the churchmen. Well, quite naturally, they didn't understand him, and they decided, well, to punish him. What they did, they tortured him, they imprisoned him, and he found himself in a situation when he knew all the right answers. It's just the right answers were not available. It was like that, right? He knew the right answer, it's just the right answer was not available. So what do you do?
Call a friend.
Call a friend, exactly. Luckily, he had friends. And with the help of these friends, like Copernicus and Newton, he managed to liberate science from religion. Hurrah! And that's where the real science began in the 17th century. They created the so-called scientific method. And with the help of this scientific method, they proved new and new theories. They discovered more and more facts. So that brought us to the contemporary science. And in the contemporary science, what have we? We have experiments, observations, none of that metaphysical nonsense about gods and religion and all sorts of things. Just experiments and observations. Nowadays, scientists believe that God does not exist. And finally, it is because of this scientific method that science is a rational activity. And it's this scientific method that allows us to demarcate proper science from pseudoscience. In a nutshell, my dear friends, this is what I think any educated high school kid thinks about science. This is pretty much the popular mythology of science, abundant everywhere. Watch science documentaries, read popular science literature, open science textbooks. This is what you get. Well, probably, you know, if you skip the Lord of Light part, everything else you pretty much get in abundance. Now, this was a story. But let's now try to be philosophers here and try to extract the basic myths on which this story is based. And this is exactly what I'm going to do now. Myth number 1, science was created in the 17th century. Basically, that there was no science before that. This is myth number 1. Myth number 2, Galileo was a martyr of science. Basically, he was tortured and he was punished and he was treated unjustly. This is the second myth. The scientific revolution liberated science from religion. This is myth number 3. Myth number 4, the contemporary science believes that God does not exist. And myth number 5, that contemporary science is all about observations and experiments, that it has nothing to do with metaphysical stuff that we cannot observe, that we cannot measure. It's all about observations. This is myth number 5. Myth number 6, science proves things. Myth number 7, the method of science is universal and unchangeable, meaning that the way we do science nowadays is the same as we used to do it 200 years ago, and it's exactly the same as it's going to be 300 years from now. It's unchangeable. Myth number 8, science is a rational enterprise because of its universal method. 9, each succeeding theory encompasses more and more true facts. And finally, myth number 10, there's a strict demarcation line between science and pseudoscience. These are the 10 myths. I'm going to zoom out. If you pay attention, 5 of these myths are historical, and 5 of them are philosophical. Now my question is, does any of this hold water? Does this make sense? Is any of this true? Now that I told you that these are myths, you might be inclined to say, well, no, I never believed in this. It's only you, Jakob. But let's be honest here. How many of you, before my telling you that these were myths, would subscribe to something like this, give or take? How many of you? I like to see many brave people here. Very good. Now the thing is, this question here cannot have an answer unless you study history and philosophy of science. And that's why you need history and philosophy of science, to avoid ignorance. When you get people, very educated people, famous scientists saying everything right as far as science is concerned, but once they get to the history of science or philosophy of science, and they talk about these things, and you say, you cannot be this uneducated, can you? What we're doing here, we're fighting against basic ignorance. I'm going to skip philosophy for now. I'm going to start with history. What do we mean by history of science? I'm going to give you 2 options here. Option number 1. Biographies of great scientists, intellectual biographies rather. Guys like Copernicus, Galileo, Newton, Einstein. This is one thing. On the other hand, you also come across histories of scientific institutions. What are those institutions? You can have universities, like Bologna, Paris, Oxford, Cambridge, University of Toronto, why not? Or it could be other institutions, like European Organization for Nuclear Research, CERN. Then you can have the history of Royal Society, you can have the history of the German Academy, and so on and so forth. So you have 2 options. Which one of these you think we're going to study? Biographies of individual scientists or scientific institutions? Which of the 2? Okay, so how many of you think that it's intellectual biographies of individual scientists that we're going to focus on? How many? All right, quite a few. And how many of you think that we're going to focus on scientific institutions? Even more. Well, I'm sorry to disappoint you. The right answer is neither, because there's the 3rd option. And the 3rd option is scientific theories. That's what we're interested in. People, institutions, papers, journals, articles, magazines. It's all science, to be sure. But the real essence of science, its product, its outcome, it's its theories. That's what it's all about. It's not about, just putting people together, having conferences. That's not real science. Real science is the outcome, and the outcome is the theories. And that's the interesting part. So basically what we are interested in, changes in the mosaic of accepted theories. So what is this thing, the mosaic? I'm going to give you the outline of a contemporary mosaic. If I asked you, what is it that we accept nowadays? What theories do we accept as the best available descriptions of reality? Basically, what is it that we teach our students? You'd probably say, well, a couple of physical theories, quantum physics, general relativity, cosmology, Big Bang and stuff. What else? Some chemistry, some genetics, some biology, neurophysiology. I'm going to miss some of the sciences, so I have to apologize. There wouldn't be enough room if I portrayed each and every one. And then some social sciences too, some psychology, sociology, economics, history, right? Mathematics. Basically what we have here is a mosaic of different scientific theories. And these are the theories that we nowadays believe provide the best available description of the world. Some of these theories belong to natural science because their object could be a physical reality, chemical reality, biological phenomena. It's all natural science. Even human body, human anatomy, the study of human body would be natural science. Then you get to social science, and social science would include everything that has to do with human beings, creation of the human mind. And in addition to these two, you have formal science. And formal science, these are basically logic and mathematics. These are the sciences that deal with formal objects, numbers, so on and so forth. So you have natural science, social science, and you have formal science. I'm going to give you a few definitions now. So what's a theory? This here is a sign of a definition. A theory is basically any set of propositions. It can be comprised of thousands of different propositions, like when we say Newtonian physics or classical physics, thousands and thousands of propositions. Or in an extreme, it could be comprised of one proposition, when we say theory of flat Earth, which only says that the Earth is flat. Or the theory of spherical Earth, which basically says that the Earth is a spheroid. So at the extreme, you can have the one extreme, you can have a theory comprised of one proposition, or you can have very complex theories made out of thousands of propositions. These are all theories for us, okay? Now, you have many accepted theories, put them together, what do you get? You get a scientific mosaic. And this is your definition of mosaic. Set of all accepted theories. And this sign here, by the way, do we have any computer programmers here? Or any future computer programmers? Do you know your UML, Unified Modeling Language? So this sign here shows that scientific mosaic is made out of theories, consists of, that's the sign. Is this clear, this relation? Very good. And finally, this brings us to the concept of scientific change. And this sign here is the sign that we use the concept of scientific mosaic to define the concept of scientific change. What is scientific change? Any transition in a mosaic. Whenever you switch from one theory to the next, you have an instance of scientific change. I'm going to give you a few examples. It's a historical fact that the scientific mosaic was not always like this. We're going to take a timeline, 100 years ago, 200 years ago, 300, 400, so on and so forth. Now, if we went back 250 years ago to the middle of the 18th century, and if I asked you, I say, go and check what educated people of that time period would study in their schools, universities. I'm not talking about laymen. I'm not interested in vox populi. Vox populi is not always vox dei, as you may know. We are interested in the opinion of the educated people, people like you. If you were born in the 18th century, and if you were to go to the best universities of the time, let's say Paris or Bologna or Oxford or Cambridge, whichever, what is it that you would study back then? So this is what comprises the scientific mosaic of the time. You understand? It's not the opinion of the layman. It's the opinion of the educated people, the scientific community. And back then, you wouldn't recognize anything. Well, probably recognize some things. Here, if we zoom in, you'll probably recognize calculus here, which is still part of our contemporary mosaic. But everything else, pretty much everything else, is different. In the middle of that mosaic, you have the Newtonian physics here, which we still use, but we no longer accept. I'm going to explain it later. We use it, but we don't believe it's the best available description of reality because we have quantum physics, general relativity. What else you have? You have phlogiston theory of combustion, which is the idea that pretty much everything that has a capacity to combust, to burn, it's because there is this internal substance, this internal principle called phlogiston that makes things combustible. Then have a look at this thing here. This is the theory of preformation. This is the idea that human beings are created as fully formed organisms with limbs and everything. Even in a male semen, it's fully formed. You see here? It's basically in this position here. That's what it does. So this was the theory, that human beings are preformed and the only thing that happens to them, they grow in size. You know, just like tiny pizzas, you put them in a microwave and they grow in size. Now pay attention to this tile here. Theology, study of God, was part of the scientific curriculum. Now you would say, well, wait a second, this is religion, right? This is not real science. Nowadays, yes. Nowadays, if you say, well, you know what, I have this interesting idea of a project. I want to apply to a grant agency because I have a way of studying attributes of the Creator. In particular, I want to tackle the question as to how many angels are there. Do you think you're going to get a grant? Chances are you're not going to get anything. We have a theology department these days, but pay attention that nowadays when we say theology, that's not exactly the same theology back then. There are two different meanings to the word theology. One is theology proper, which is study of God and His attributes and His works and so on and so forth. This is the classical sense. And the second sense is what we nowadays often call religious studies. Study of different religions, different religious attitudes, history of religion. That scientific discipline, theology in this latter sense, is still part of the scientific mosaic. It's just a historical discipline. It's part of history, right? It's part of history. It's part of cultural studies. That's what it is. But theology proper, the belief that God exists and belief that God is the creator of the universe, is no longer part of the mosaic, but it used to be. So in the 18th century, they believed that the earth is spherical and they believed that the God created that earth. It was on the same level. It wasn't like he was a scientist here and he went home and he was a religious person. No, it was part of the same thing. They believed that the God exists as much as they believed in the laws of Newtonian physics. It was the same for them. So it shouldn't come to you as a surprise that guys like Descartes and Newton and all of the 18th century, they all believed in God, with some exceptions obviously. But the accepted view, what you would study if you went to Paris University, Oxford, or anywhere, you would study theology. It would be part of the curriculum. Now, zoom out. 500 years ago, this is the late medieval period. Here, I promise you wouldn't recognize anything. Or maybe only this thing here, Pythagoras' theorem. You would probably recognize that. But everything else, absolutely different. In the center, you have the Aristotelian theory of the four elements. I'm going to explain it shortly. Then you have geocentric cosmology with the earth in the center of the universe. And pay attention to the next tile. This is astrology. So, whoa, wait a second. Astrology was part of scientific mosaic? Yes, it was. It was part of the scientific mosaic. In fact, if you were going to become a physician in the 15th century, 16th century, even in the 17th century, you were supposed to know your astrology. Again, I'm not talking about laymen. I'm talking about the best minds of the time. Isn't this shocking? Astrology was part of the scientific curriculum. So, what have we here? It's safe to say that the scientific mosaic changes through time. And I'm going to give you only one example. I'm going to move all these things. And let's take a very simple case, a falling apple. And the question here is, what's going on in here? Why does it fall down? Very simple question. You'll be surprised to find out that even this very basic phenomenon has received many different explanations throughout the history of science. I'm going to give you the Newtonian, the Aristotelian, and the contemporary Einsteinian explanation. That's what I'm going to give you. I'm going to start with a basic textbook example. Newton's physics is not difficult. Newtonian physics, zoom in, Isaac Newton himself. And you'll say, well, it's very simple. Everyone who knows the foundations of my theory will tell you what's going on here. You have two objects, the Earth and the apple. The Earth has a certain mass, the apple has a certain mass, and we know from the law of gravity that two objects with mass must attract each other. It's very straightforward. The force of gravity pulls them together. This is what happens. Simple? You all know this. Now, if Aristotle was alive, he would say, well, this doesn't make any sense to me. This is not what's going on. In fact, what's going on is something completely different. And this is the Aristotelian view on the subject. So first and foremost, you have to appreciate that the universe is made out of two distinct regions. There are two completely distinct regions in the universe. The Earth is in the center of the universe, says Aristotle, and all the planets, they revolve around the Earth. So you have two regions. You have the celestial region here, and everything in the celestial region is made out of the so-called quintessence, the fifth element, element ether. And it's in the nature of this element to revolve around the center of the universe. So this is the way they explain why planets move. Why do they move in circles? Well, because they're made out of the fifth element, the quintessence. When you get to the terrestrial region here, everything in this region, and this is pretty much the Earth, the air around us, all the way until the sphere of the moon. That would be the so-called sublunar region or terrestrial region. Everything in this region is made out of 4 elements: earth, water, air, and fire. And if we zoom in this region, 2 of these elements, earth and water, were thought to be heavy. The 2 other elements, air and fire, were thought to be light. The difference is essential because they believe that everything that is made out of heavy elements has a natural tendency to descend towards the center of the universe. That was the basic principle of their physics. When you let things go, heavy things go, why is it that they go down? Well, because they have a natural tendency to descend towards the center of the universe. For light elements, the situation is the opposite. Everything made out of air and fire has a natural tendency to ascend towards the periphery of the sublunar region. So basically, when you fire a match, the fire goes up. Why is that? Well, because it has a natural tendency to ascend. If you drop a stone into water, why does it go down? Well, because earth is heavier than water, and therefore things that are made of earth should penetrate through things made of water, and therefore they'll go all the way down. Very straightforward. So if you take this, then you can explain what you see around us. In particular, this explains why the earth must necessarily be in the center of the universe. Because if your basic physics tells you that everything made out of earth collects in the center of the universe, then where else could the earth be? So you don't get a choice here. You can't accept the Aristotelian physics and think of, maybe we'll abandon geocentrism and accept some heliocentrism, the sun in the center. You can't have it. You can't have it both ways. Okay? So the first layer is that of earth, then comes the layer of water, then comes the layer of air, then comes the layer of fire. If you apply this physics to our basic case of a falling apple, how would Aristotle explain this? So very straightforward. The very fact that the apple goes down tells us that it's made of heavy elements. It's some sort of a combination of earth and water, right? That's what it indicates. And as a heavy object, it must descend towards the center of the universe. It's very straightforward. This is what's going on. No gravity. The only thing that the apple must know is the position of the center of the universe. That's the only thing that everything in the universe knows. Where the center of the universe? There it is. Okay, so I have to go there. That's it. So for an Aristotelian guy, the whole Newtonian idea of everything in the universe attracting each other would be ridiculous. Now, for the same phenomenon, you have 2 explanations. The Aristotelian explanation is that the apple, the heavy object, descends towards the center of the universe. And the Newtonian explanation is that the earth and the apple attract each other because of the gravity. 2 different explanations. The first one accepted all the way until the early 18th century, all the way until the late 17th century, early 18th century. This is what was accepted. Then for the next 200 years, the accepted view was that of Newton, all the way until the 1920s. And the contemporary view was suggested by this guy. He's remembered for the theory of general relativity. Einstein would say, let's take a fragment of space. The arrows here and the lines, they indicate the light rays, rays of light. This particular fragment of space will be flat because there are no objects, and therefore light rays travel in straight lines, as you can see. Now the question here is, says Einstein, if we had a massive object, let's say a star, let it be our own star, the sun, what would happen to the fabric of space? What would happen? And Einstein says, if you had a star like the sun, it would curve the space around it. In reality, it's space-time, but I'm going to keep it simple for now. It would curve the space around it so that everything, including the light rays, would bend when traveling in the vicinity of this object. This is something new. This is something unpredicted by Newton. This was the new prediction of Einstein's theory. So this is very similar to when you have a suspended bed sheet, and you put a ball, let's say a basketball, in the center of it. What happens to the bed sheet? It gets curved slightly. Well, depending on how suspended it is, but it gets curved. And you have a ball here, let's say a basketball, and you take a smaller ball, let's say a tennis ball, and put that in a vicinity of that bigger ball. What's going to happen to the tennis ball? It's going to seem like there's an attraction between the 2. Like there's a gravity that attracts the tennis ball to the basketball, right? That's what's going to happen. What would happen if we had an even heavier object? let's say, more massive object, like a black hole. In the case of a black hole, the curvature of space would be such that nothing would be able to escape. This light ray here would be able to escape the curvature, but here, nothing would help it. Now, if we apply this theory to our fundamental case of a falling apple, Einstein would say, well, it's very simple. The space around the Earth is curved due to the Earth's mass. The curvature is not great. You can't compare it with the curvature produced by the sun or, God forbid, the black hole, but there is some curvature. So what happens with the apple? Same thing that happens to that tennis ball, seemingly attracted by the basketball. The same thing. So there's no gravity. There's no such thing as two things pulling each other. There's no such thing. There's an inertial motion in a curved space-time, just like a tennis ball. Okay? Your name is?
Miriam.
Miriam?
So, no offense to Einstein, but to me, the theory seems most circular because the example you're giving relies on gravity to understand. So the bowling ball is pushing down, right?
Very good. Any response to this? You understand the point Miriam is making. So the point she's making is that basically that metaphorical example that I brought up with a suspended bedsheet itself relies on the concept of gravity. Anyone wants to reply? Rob?
My name is Rob. I completely agree. And from my understanding, it's just a really simplified example to help people understand this super complex theory of relativity and curved space-time. But you're absolutely right. It does rely on Newtonian gravity to help you understand Einstein's gravity.
Very good. That's exactly the case. Now, I hope you understand that silly example that I brought up. I didn't come up with it, but it's a common example to help people to imagine the curvature of space-time, which is not an easy thing to imagine. And the problem with all those examples that we have, there are many of those. Many of them rely on classical notions, on notions of classical physics, just like gravity, and it was very good of you to point it out. Now, what I want you to get from this long story is not so much the theories themselves. Appreciate the fact that for the same phenomenon, you can get more than one explanation. And these explanations, these are not some random explanations. These are the theories that have actually been accepted at different times of the history. I'm not talking about some rubbish explanation that somebody came up with. No, these are the things that people would study in the universities. And our theory has only been accepted for about, 90-odd years. Compare it with the Aristotelian theory, accepted for almost 2,000 years. And Newtonian theory, accepted for more than 200 years. I'm not asking you to accept these old theories. There's a reason why we no longer accept these theories. What we have to appreciate here is that there is scientific change, that science changes through time. Is this clear? Very good. This brings us to two fundamental questions of the history of science. If you're a historian, then it becomes your task to pick a date, and for that date, you have to be able to reconstruct the mosaic of the time. Let's say you're interested in the second decade of the 16th century, 1510s, and you're interested in particular in the Oxford scientific community. So what do you do as a historian? You delve into archives, and it becomes your task to unearth, to reconstruct what people back then thought about the world, thought about the universe. Isn't this fascinating? This is what historians do. The second question, which immediately follows the first question, okay, you know what happened here, and you know what happened there. What about the transitions? You have the snapshots. You know the mosaic around 1510, and you know the mosaic around 1520. What about the transition? Why is it and how is it that scientific mosaic changes through time? So two questions. And basically, this is the history of science. Any questions so far?
Probably going to be one of those stupid questions erased in post-production.
Your name is?
Vanessa. Was alchemy ever a part of the scientific mosaic of any
That's not a
period of
stupid
time?
question. That's actually a very good question. We're going to talk about alchemy in lecture 6 when we deal with science and pseudoscience. But the short answer is not as far as I know, no. It was considered a proper scientific enterprise. It was considered something worth pursuing. But insofar as I know, there was never a point when alchemy or any alchemical theory was part of the scientific mosaic. It was never a part of the official curriculum. But then again, the idea that you can take some basic metals and transform them into more noble metals, like gold, for instance, preferably gold and more gold, this idea was considered quite viable. And there's a reason why. It followed from the Aristotelian physics of the time. Now, what does philosophy of science have to do with all this? We have historians, and historians study the history of science. Why would you need philosophy for? What's the point? You know what they say about philosophy? I was actually told this. This is an old joke, but I didn't know about it. Don't look at anything in the physics lab. Don't taste anything in a chemistry lab. Don't smell anything in a biology lab. Don't touch anything in a medical lab. But most important of all, never listen to anything they tell you in a philosophy department. And there I am. I ended up teaching philosophy of science. Now, why philosophy of science? If you ask my opinion, of these two sister disciplines, history of science and philosophy of science, it is true, of course, history of science is very interesting. And it's really fascinating. You study different ideas in different time periods. It's very interesting. But without actually trying to unearth the mechanism of scientific change, without trying to understand why things change the way they change, it's interesting, but not so much, at least not for me. You see, I have a theoretician's mind, and I want to understand how things work. Whatever I look into, I really try to understand not just what happens, but also why it happens. I try to understand the underlying mechanism. And for this, you need philosophy, philosophy of science. Question number 1. We know that scientific theories change. We've seen one example, transition from Aristotle to Newton to Einstein. You could take any scientific discipline. Let's take astronomy. It's the same thing. Transition from geocentric astronomy, then Kepler's astronomy, ellipses, and then contemporary cosmology and astronomy. You can take any field you want. You have a case of scientific change. Now, the question is, does everything in the mosaic change? Or are there things that are immune to change? Are there such things that once in the mosaic, stay in the mosaic forever? Or are we in a position to say that everything is changeable? So this is the first question. Another way of putting this is, can we know anything for certain? Or, the same question, is there such a thing as absolute knowledge? This is the question. It's question number 1. Again, what I'm asking you to do, I'm not asking you to come up with an answer on the spot. What I'm asking you to do is to appreciate the question. Okay? Question number 2. We have different theories. How do we evaluate these theories? How do we accept some theories and reject some other theories? In other words, what is the method of theory evaluation? What criteria should any theory satisfy in order to be accepted in the mosaic? This is a philosophical question. For instance, nowadays we accept general relativity. Why general relativity and why not the Aristotelian physics? Certainly there must be a reason for that. So what is the reason? Understand the question? Very good. Question number 3, scientific change. Theories change. Is there any logic in the change? What's the mechanism of scientific change? Why is it that we abandon some theories and accept some other theories? Is this because we just get tired, just like it happens in fashion? You know, when you buy yourself new clothes, not necessarily because you didn't like the old ones, but because you just need something new, not necessarily better. Scientific change. Is it similar to changes in fashion, or is there something deeper? You understand the question here? Is there a logic? In other words, what's the mechanism of scientific change? That's the question. Question number 4, that's the question of scientific progress. After all these changes, after all these transitions in the mosaic, we've seen many cases when theories accepted for centuries or even millennia were eventually abandoned. Take cases like Galenic physiology. This is a theory that human body is made out of 4 bodily fluids. This theory actually stayed in a mosaic for about 2,000 years, and yet it's no longer accepted. Then another theory is classical geocentric astronomy. This one, again, accepted for more than 2,000 years, and now rejected. So the question is, if it is the case that even time-honored theories eventually become rejected. And we know this from the history of science. Is there such a thing as scientific progress? Are we moving towards anything? Are we getting any better? You understand the problem here? You can't say, well, our theories, as opposed to the theories of the past, are the true theories. This would be very presumptuous, wouldn't it? Even the best of our theories have been accepted for no more than 100 years. That would be very presumptuous of us to say, well, no, now we know for sure. Those guys were all mistaken. The history shows that a theory accepted for 2,000 years was eventually abandoned. Are we going to take the risk and say, no, 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 we know for sure? So the question here is there such a thing as scientific progress? That's the question. The fifth and final philosophical question that we're going to tackle in this course concerns the difference between science and pseudoscience. If you look at the history of the scientific mosaic, you would come across many theories that were once part of the mosaic and nowadays not only rejected but also considered unscientific. There are theories that are rejected nowadays but still considered scientific. Let's say in Newtonian physics, we no longer accept it, but if you ask anyone, they say, oh, it's a proper scientific theory. No longer accepted, but still scientific. But then again, we had theories like astrology. When we rejected the classical astrology, we didn't replace it with some new astrology. We just rejected the whole discipline. And now we consider astrology as pseudoscience. You know, it's an interesting thing, and my friends here know that I'm very much in the business of using astrology because it's fun. You know, you say, oh, I know you're typical Sagittarius there, Greg. We do these things because it's fun. But when it comes to distributing PhD degrees, we say no. You can't be a PhD in astrology. That's impossible these days. So, you had astrology, another case of a theory accepted for a very, very long time and then nowadays considered unscientific. Theology. Theology was part of the scientific mosaic, nowadays no longer. Now the question is there such a thing as a clear-cut line between science and pseudoscience? Is there such a thing as a demarcation criteria? There you have it, your 5 philosophical questions regarding science. Is there absolute knowledge? How do we evaluate our competing theories? What is the mechanism of scientific change? Is there such a thing as scientific progress? And what is the difference between science and pseudoscience? 5 philosophical questions. Any questions about these questions?
My name's Ian. I was wondering, how does something change from pseudoscience to accepted science or real science, if you want to put it that way?
So Ian's question is, how is it that something changes from pseudoscience to science, and the other way around, I guess, too? This would be a very good example of a philosophical question. To understand that, this would be your question number 3. What's the mechanism of scientific change? Is there any logic in these things? You see, if you ask philosophers, you're not going to come across one single unified answer, because unfortunately nowadays we don't really have a commonly accepted theory of scientific change. But we're getting there. In lecture 4, you are going to study one such theory that presumably explains why and how we switch from one theory to another, why and how it happens that a theory that was considered scientific for thousands of years ends up in a trash bin. I have to wait for that. Any other questions? Okay, very good. So next time we're going to start with the first question. And this is the question of absolute knowledge. Can we know anything for certain? Any other questions? Is this fine? Okay, do you think you could tolerate me for more than 1 week? I was very glad to see you all, and I hope to see you all next week. Have fun. Thank you.